All right, everyone. Welcome to the stream of the November 2025 monthly puzzle. So this puzzle was the title was "Mind the Input Delay," and it was made by ToughThought. So I guess I'll start with a quick description of the puzzle. So there's a little bit kind of going on the screen, but the essence is not too complicated. Um, you've got these two inputs, both of these reactors, each of which have the same layout, 8 bonders and 1 sensor. Um, uh, yeah, they've got the same inputs, but the difference is that the inputs at the top have an input delay of 1, which means they constantly come in, while on the bottom they have an input delay of 10. And this is kind of one of the big things to deal with in the puzzle, as do you try to do something different between the reactors, and in general, it just kind of complicates things. And then these things in between, essentially all they do is they make sure that you can only pass the molecule as shown here. And then these last reactors really only serve to then merge those outputs. Yeah, and in general, we'll see a little bit going on in these, but nothing too crazy. Just kind of to set something up, I'm going to, and you guys can all see this fine, right? I'm going to refer to the reactors, just to make this easier, as Reactor 1, Reactor 2, Reactor 3, and Reactor 4. This is probably not the best ordering, but it's simply what I've gone with when thinking about the puzzle, so we'll keep doing it here. All right, so let's get started with a solution from Greasefire, I believe Teti on Discord, with Best I've Got. Well, that's all right. So let's see what his solution does. So let's see if I remember this. Yes, okay. So he does something we'll see again multiple times later. I believe this exact input ratio is used by a lot of people. But essentially, we notice that this top, so okay, we've got our two outputs, right? Nitrogen and nitrate. And the thing that he notices is that we can sort of very quickly get nitrogen off of this top molecule. We yeah, it's quite easy to remove the oxygen, and then simply we pretty much have the output from there. And then we can take the rest of it and bond it into this nitric oxide, and that gets us the output. So, and we'll see also he does the exact same thing in the bottom reactor. So the two reactors are identical. And yeah, it's a pretty nice, good, simple solution to get us started. I think, so yeah, and oh, and let's also look, so those were reactor 1 and reactor 2. Let's take a look at reactor 3 and 4. These are also relatively simple. We're sort of just varying the inputs all the way over. And then down here, we're doing the same sort of thing. And yeah, in both, we just make sure that there can never be collisions by making sure the paths never overlap. But yeah, it works pretty well. Let's actually just run it through real quick. All right, 605 cycles. All right, and so I guess kind of, yeah. Well, actually, yeah. So that was Teddy's solution. As always, thank you. I sort of put a hand of thanks out to everyone who submits to a puzzle. These are, I think these last two have been like not too crazy difficult of puzzles, but it's still always like great to see new players uh, give a try, and we'll see this like we will see this like same sort of idea come back, just more refined in later solutions. So congratulations. I will also say actually that I personally did not see this way of solving it, and it will sort of inform multiple things about the puzzle. Yeah, so this is Teddy's solution, but or grease fire. Um, so yeah, we'll I guess keep moving forward. All right, and we go on to Astro Nelson's solution of nitroslus. Ah, yes. Okay, so his solution. Yes. Okay. This is also yes. This is a very nice idea. So what? Okay, what Astro Nelson is doing here is we we just decided to ignore the top input, and there's a couple reasons to do this. Um, one one is simply sort of a travel time thing. If you can say just around one input, then that's kind of good. We can see this really nice way of constructing the output that we'll see a lot of other solutions do, which is if we notice that if we do this step right here, where we take an input, get another input, and then do a minus and bond at the same cycle, the result we have is we have a nitrogen here, a double bond to an oxygen here, and then an oxygen off the bottom. And we'll notice that that's almost exact, like that's the 3/4 of the like output we're going for. So essentially what Astro Nelson does, and what a lot of other people are going to do, is start with this sort of arrangement, and then um, try to sort of deal with the last output however is necessary. The way Astro Nelson does it here is he sort of drops this nitrogen off here, and then slowly sort of separates out the molecule and has blue come in to finish off the necessary bonds, and also finish off the last bond for the nitrate. This is quite a nice solution. But yeah, so that's reactor 1. Let's now take a look at reactor 2, see what he does here. So this does, it's the same, we're going to be only using nitric oxide, but it's going to be done a bit differently. So here, and the reason we're doing it differently is that we could probably try to make something work with this, but it's kind of annoying with all the timing, because you need to time things nicely, and there's also because actually let me this might be a good thing to talk about because it's very relevant to this puzzle. So in general, when I'm discussing cycle solutions, I'll usually talk about throughput and latency. And when I say throughput, that's sort of the cycles per output, the rate that you're producing outputs, and then latency is sort of the added delay. And there's a lot of reasons that you might have added delay. And both of these are important to minimize in cycles. Depending on the puzzle, one might be more important than the other. For instance, the last puzzle, latency was much less of a concern. Whereas this puzzle, it's kind of just as significant. Or, well, wait, not just as significant, but it's sort of something to be considered. I know at least I spent a decent amount of time working on improving that. And based on how close the top 3 results are, it was definitely worth it. But all right, let's talk through. So I guess how is that relevant? This puzzle, I believe it's relevant to his solution here. Let me check though. We'll actually have to see. So here is this relevant? Okay, yeah, I think it's yes. Okay, so one way you could see it's sort of relevant is even though yeah, so the reason, yeah, one reason we kind of do this differently is that everything's a little slower, so we can try to, well, okay, actually, no, I think it's, yeah, actually, I think here it'd be better to try to do something similar to this, but either way, yeah, I don't think it's really capitalized on here. What I was going to say is that you can try to, if you know that everything's slower here, you can try to make it so that this last input you get, the sort of one you're waiting on, you sort of run through the steps quicker for it. But it doesn't seem like Astronelson really does that here in comparison. I don't think it's much like faster than how quickly he goes from the last input to outputting between these two reactors. But either way, so yeah, they do a similar sort of thing of yeah, taking these uh, same input ratios um, of yeah, just only using the bottom output. So far, I guess to um, yes, to let's yeah. Let's actually write this out. That'll be useful. So let's sort of write out what we've seen for the ratio so far. So from um, we saw two uh, yeah, we've seen this is what Greasefire did. And we'll see some other solutions too. And then well, I guess let me actually write out the full ratio. So what Greasefire does is he takes this and makes I believe it's yes. So two nitrogen and one. Let me leave more space for this. Okay, because we'll see a lot of different approaches, and yeah, it's kind of an interesting reference point. So, and then what Astro Nelson does is he does this. One of the things to notice is that even though Greasefire makes more nitrogen, they make the same amount of what's it called? Nitrate um, in both solutions. Um, and you can actually and you'll notice also that both of them make as much nitrogen or more than they make nitrate. And so you can actually from the ratio or from the inputs check that nitrate is always you're always going to make at least as much nitrate as you are nitrogen. So it's kind of the limiting factor for most solutions, or I think I would believe all solutions. Um, but you can have this specific situation where they're exactly equal. But most of the solutions we're going to see are going to be uh, waiting on nitrate because in order for the puzzle to complete, you just need 40 of each output. And so whichever one gets to 40 later is the only thing determining the cycles. Yeah, in this case, with Astronausen, we can see both of them are making sort of the same um, yeah amount of nitrate per sort of I guess input group. I think for let me check their exact cycle loops. Um, check that real quick. Let me find that. Okay. Yeah. All right. So yeah, I'll write this out as well. So you've got that Astro Nelson is running this. Okay. Yeah, so 18 cycles, 30 cycles, and then this fire was, I believe, yeah, 21 cycles, 21 cycles. Okay. So what I'm saying there is this will refer to reactor 1 and this will refer to reactor 2. So Astro Nelson has a significantly faster reactor 1, and that's kind of the reason he wins here. But it's actually worth noting that Greasefire actually has a better reactor 2 here. And we'll see, we'll actually see a lot of solutions have a lot of variance in being one better than the other and whatnot. But all right, let's keep moving forward. Oh yes, let's actually run. Oh, and let's see if yeah, and you can see Astronauts does something very similar to what we saw before in the lot in Reactor 3 and Reactor 4. General, I think I'll stop looking at Reactor 3 because basically everyone does this if I remember correctly. Whereas Reactor 4 we'll see a little more variance in. Again, because as I was mentioning, nitrate is the limiting factor. So even it often doesn't matter as long as you're going fast enough on the nitrogen, it's sort of fine. And whereas nitrate, you want to get like the last output to the output as quickly as possible. So there's a little more to be careful with there. But we can see Astro Nelson finishes with 481 cycles. All right, let's now move forward on to Pre's solution. Upper 16, lower 27. Let's see. All right. Okay, so Pre does the same ratios, at least for this reactor, as we saw with what was it saying? Yeah, same ratios as same ratio for this reactor as we saw with Astro Nelson. I guess down here, okay, we'll look at that one in a minute. So here it looks like I guess I'll trust what he wrote in the title for 16 cycles. This is actually one I haven't seen yet, so but I guess I can sort of check it. Yeah, okay, 16 cycles per. So we can see that, I guess, how do I want to write this? Maybe I'll sort of I'll try to list it like this, and we'll see how this goes. There will be a bit to write. So now, okay, so Pre's solution now is going to use, Pre's reactor 1 is also going to use this ratio, and he's going to do it on a 16 cycle loop. So we can see a little bit faster than Astro Nelson. Now let's check out this second reactor. Okay. Yes, okay. I think me and Pre did almost the same. We did very similar things. So it's fun to see. Okay, so Pre does, I believe, is this, let's see if this is a new issue for us. Let's actually show both. Okay. Yes, we've now got a new ratio. Using 1 2 or and 1 and 0, and then producing, or sorry, 2 of those, and then producing 1.5 into, I guess actually I'll write it out with integers. So 3, 2, 4, and 2. So we'll see actually, yeah, as I was mentioning, we'll see this one with mine, and pre runs his reactor 2 at, yes, at 27 cycles. So we can see pre has both, yeah, now has the fastest solution for each of both reactor 1 and reactor 2, as what we've seen so far. Let's see. Yep, reactor 3 is sort of the same as usual, and reactor 4 is also nothing crazy. So let's run it through. Let's see. Cycle count he gets. So 434. Which is, yeah, a bit better than 50 more than astronauts. And yeah, let's actually maybe look through this a little bit harder. So I realized I skimmed over. Yeah, I've skimmed over a little bit of the details. Maybe let's actually look at exactly how he's doing some of this. So here, yeah, I think it's kind of, I like this. It's kind of an interesting idea of this sort of pinwheel solution. I think it's a bit different than how I approached it. Um, let's see. Yeah, sort of. Yeah, one of the big challenges that I at least found with this puzzle was the monitor count. Sort of a you want to do more than you like, more than you have. It was something yeah, it's hard to work around. But all right. Yeah, so we do this kind of nice pinwheel thing, and then we sort of blue manages this extra nitrogen. Make sure so this sort of like at 1 we keep, because we do we get 4 nitrogen when we do 1 input here and 2 here. We can't evenly make a nitrate and some amount of nitrogen, so we have to split it across 2 loops. So that's kind of the main thing blue is doing here. But yeah, and then this was just sort of a nice loop to do this reactor. Just sort of, in some ways, similar. It's actually pretty different from astronauts. I guess he's more. This is more. Yeah, there's a little bit of a handoff, and um, again, this sort of pinball idea. It's kind of interesting. Oh yeah, yeah, yeah. My ratio is wrong. Let's see. 2, 3. No, I believe this is correct. Maybe I'm missing something, but I believe that's correct. Okay. Let's see. Blue does not always replace the first. Oh, wait. Oh, wait, you're actually right. Okay, I guess I misunderstood. So, oh, you're totally right. I misunderstood. Okay, so you do. So these 2 times you do this, then the third you do something different. I see. Okay. Thank you. Yes, you're totally right. Okay. Yes, that's a little more complicated. So the first, yes, that makes a lot of sense. Okay. So the first loop, okay, we'll see the first 2 loops, blue sort of helps out. Or blue brings in this nitrous oxide, whereas the third loop, blue actually doesn't. It's just nitric oxide. So this the ratio here is actually 3 and I think that should be no. Yeah, 2 and then 7. Okay, very interesting. And we make um and we make 3, 4, and 3. Okay. Okay. Yes, that's okay. Very cool. I don't think we're going to see that ratio again. Very interesting. I see. No, that makes sense. Um, yeah, it makes sense that um, that just works here. Uh, so I think you're just sort of going at a speed. Yeah. So yeah, the challenge for this reactor is trying to you can't like here we're going to see a lot of solutions just use the bottom out input. Not all actually, but a lot of them. Um, but that's not going to be possible here because otherwise you would be constantly waiting on the bottom output. So people have to come up with more creative solutions. And one option is certainly this one. And I guess no, still the loop. Okay, so I guess it's, yeah, red runs on a 27 loop. So that means that this is 81 for the entire loop. So every 27 cycles, we're making a nitrate. Okay, very interesting. All right. Um, yeah, no, it makes pre-states part of why it's so bad is that blue can't keep up with red, so I have to skip the replacement trick for every third NO3 output. Um, yeah, I think the problem is sort of once I actually also have a problem with this. And yeah, you'll see in my solution. Yeah, I also had something very tight. Um, but once blue's here, my guess is it would take too long for blue to get back to the thing, and so it's simply faster for red to just start with the next group. Um, but yeah, makes sense. All right, very nice. Let's move on to, all right, yes, we went through that. Let's now move on to Yellow Bunny's solution, 425.104. Oh yeah, the exact metric was cycles plus symbols over 1,000. So you can deduce both the cycle and symbol count from that. Let's see what he does. So for Yellow Bunny's reactor 1, we see something reminiscent of what we've seen before. So this is the same, um, let's see, how does this ratio compare? Yes, this is the same as grease fire's ratio, where we're using the fact that um, we can very quickly make nitrogen. Um, and so what we do is we simply just sort of take that to a further extent. Pull out nitrogen as quickly as we can by processing 2 of the nitrous oxide at the same time, and then pick up a nitrate from that. So this, and we'll actually see that, oh wait, this is a little different. Okay. All right, yeah, but yeah, so we then, yeah, we do this here. I believe for this reactor, I believe we do something very similar. Let's see if I understand the exact difference. Okay. Yeah, it's sort of the same thing. I think, so the loop slightly longer? No, blue's loop is the exact same. Okay, interesting. Why? Don't really understand why these two reactors are different, but maybe Yellow Bunny can explain it to me. See, they're both sort of running on the same. Yeah, so to add this to sort of our chart as we're going so far, we now have Yellow Bunny with both reactor 1 and reactor 2 running the same ratios as Greasefire, and both at, I believe, what's the actual speed? Let's see the cycles per. Okay, so 20 cycles per. Yeah, right. That seems right. They're different because the lower one has to wait for its inputs and they output in different positions. Okay. Okay. Okay, I guess it's... Okay, that makes sense. All right. Then... Okay. Oh, the opening actually does something a bit different here. Sort of process all the nitrogen the efficient way. And then here... oh, this is nice. Yeah, so since these are timed the same, Yellow Bunny is able to... I see, yeah, this is very nice. So as I was mentioning, since nitrate is the limiting factor, we're kind of going to do weirder things in order to make sure it gets where we want it on time. And here is exactly one of those examples where Yellow Bunny uses the fact that these are timed the exact same to output much quicker. So interestingly, we can also see Yellow Bunny's reactor 1 is actually significantly slower than Pre's. But because his reactor 2 is much faster, since Pre was 27 cycles per nitrate and Yellow Bunny is 20, Yellow Bunny makes up the difference. And it's kind of close. Let's actually run it through to see the exact cycle count, and it's 425, which is just just 9 less than 3. So even this is sort of the differences where even just some small latency things can make the difference. But all right, very nice. Yeah, so let's move on from here. Now go on to Chichigal's solution of now we're cooking v3. So let's see. Let's go back to this for now. All right. Well, actually, won't be using that, so we'll just keep it like that. All right. So Chichigal's solution. Oh yes. Pre mentions that this is the first sensor use we've seen. Yeah, not many people use this sensor. I think ToughThought stated that it was he wanted it to be the main reason he gave it initially was or the one on his mind was for this last reactor to help with merging the inputs, and he said that no one used it for that purpose. So yeah, but we will see that Yellow Bunny, Yellow Bunny did use it here to simplify things, though it, according to ToughThought, it doesn't actually save symbols. But I believe, yeah, he says actually loses 2 compared to using. Oh wait, no, never mind. Sorry, I misread that. No, but yeah, it's mainly simplifying. It's not like super necessary here, but it does save symbols. But I think what ToughThought was mentioning is you can do this and it works the same, with like a slight adjustment or something. Anyways, okay. But all right, let's keep moving forward. GGGall's solution. So, GGGall's, let's start with his first reactor, and GGGall does something we've seen before, but it's very fast. So GGGall does the same ratio we saw with Greasefire, but now does it just or wait, yeah, same ratio, but just does it a lot faster. So we can see this loop is running at, this is a 13 cycle loop. So we have 13 cycles for every output of nitrate. Um, Add that onto our operating. So yeah, it's a pretty dramatic speed up. And we then see, and let's now let's also go and check out his. So yeah, I guess well, we've seen it run a little bit. Let's go and check out his reactor 2. So his reactor 2 does a very similar thing, but it's pretty much just the same thing but slowed down. So um, built it in sort of the same way, and then but it's decent. Oops. Yeah, pretty similar. I think everything is output in the exact same spots. We can see, let's now check out reactor 3 and reactor 4, see if there's anything interesting there. Looks like here he does a little bit of bonding to get rid of the stuff on top. But again, it's not super limiting. You can see actually he's building up a backlog of nitrogen here that gets worse as the puzzle goes on. But it doesn't matter because it's only 40 outputs. Yeah, that's all that we're doing too. And then here, this is merged in a pretty simple way. So yes, let's note down his reactor 2 does the same ratio, but does it because he's using so yeah, now we're really starting to run into the input delay issues. Because this is running at 20 cycles, or yeah, because there are 10 cycles between each top input, Jujigol is sort of always waiting on the top input. He'd like to go faster. He'd like to do the same thing as first solution, but he just can't. And thus he's limited to the input speed here, and thus goes at 20 cycles per nitrate output. Or I guess you could say full loop. But all right, regardless, this is still quite a big improvement. He goes at the same speed as for reactor 2 as Yellow Bunny does, but reactor 1 is much faster. So let's run it through and get the cycle count. Now 345. So this is a 80 cycle count from our previous solution. All right, let's now take a look at Dariush's solution in third place of 2 over 21 plus, or I guess 2 to 21 plus 1 to 20. And then I guess that's an average of cycles per solution, or of like cycles per output, I guess. All right, so let's take a look at what Dariush does. So in reactor 1, got the same ratio, oh yes, same ratio as we've seen some solutions do before, but we're going much faster. So we can see Dariush, builds this sort of similar thing to sort of what I was mentioning with, well, actually, no, this is a bit different. But you can see it's sort of a similar thing, sort of similar to one thing I was mentioning with Astronelson's solution of where you produce sort of 3/4 of what you're looking for almost immediately, and then you figure out how to deal with it more quickly. And instead of doing a handoff, as we've seen a lot of solutions do, Dariush does a sort of double pump solution where he has both. Waldo's doing about the same thing, slightly different. You can see Red's path is a little different. I'd assume this is to avoid sort of bad symbol overlaps where sort of the wrong things happen at the wrong time. You can see actually, like uh, ideally this loop would be too tighter, but I'm assuming that that's just not possible for some overlap of some sort. Um, so, uh, but yeah, we can see this sort of this really nice way yeah, we sort of drag everything along and then leave it in the output. And yeah, this was this the idea of just like leave two nitrogen in the output and try to bond together was something I was like actively trying with for a while. And I didn't find anything as nice as this when I was trying to do exactly that. Um, but yeah, it's a very nice and very fast way to produce nitrate. So we can see Darius does the ratio, yeah, same ratio we saw with Astronauts and Pre, um, but now uh, we're seeing it done at, so this is 21 cycles for, uh, we can see it's, yeah, 21 cycles for this full loop. So that puts us at uh, a 10.5 cycles um, per. This is right, and now let's take a look at Darius's reactor 2. And Darius does something pretty similar to what we saw with Gigigol. It's implemented a bit differently, but it's sort of the same idea. You take in 2 nitrous oxide, um, and yeah, build it in this sort of nice way that we've seen a good number of other solutions do. It's actually, yeah, so Darius actually does the exact same ratio and speed as ggBall. So we'll write that in here. All right. And now let's see if there's anything particularly special about these last reactors. Okay, so Darius does something a little quicker here. Okay, I think. Okay, I guess the ratio is pretty similar, or the amount you get from each reactor is pretty similar in his case. So he simply does this like nice bond together idea. And down here, sort of has to be a quick loop in order to deal with everything, but nothing too complicated. All right, and let's run it through. We have 308 cycles. So time spent. Pre says, I wonder if future monthly puzzles should non-obligatorily include time spent on a puzzle as a comment. Yeah, I'm actually kind of personally a little interested in that. You can try to gauge it by um, the time of submission. Because you can see the full history of when people submit if you go to the post. Um, but yeah, it's like an okay indicator. So I think Darius submitted his first draft 2 days ago. So Darius just definitely seems like a bit of a procrastinator. If I were to give a guess for myself, I actually don't know. Hmm. If I were to guess, I'd maybe say 10 hours. But that might be too high. I really don't know. Because it's sort of like spread out. And there are sometimes where I just like think about it at random times. So like I'm not actually playing or anything. I'm just sort of thinking about what might work. And I don't know. It's like hard to say. Anyways, um, let's. So yeah, that was Darius's solution. Let's now move on to uh, take a look at my solution. So, and this is fixing reactor 4, copy number 5. I had, it seems like everyone else found reactor 4 fine. I struggled with this a lot. And it was like a significant problem in my, uh, yeah, significant problem. But anyways, good for you guys. All right, let's start with my reactor 1. So, my reactor one, I do something. We'll see if it's reminiscent of what Darius does, but I do something kind of interesting. So, what I do this a similar thing to what we saw with Astro Nelson, where I'm sort of like pulling up this diagonal stick. And initially, I think something. Uh, I believe it was similar to Astro Nelson, where I did like 3 in a row. But I noticed that if you actually remove this bond here, you leave the nitrogen in a very nice spot. And I use that here in order to make quite a fast solution. So um, here, after sort of dropping this nitrogen here, I'm able to bond everything together, and I actually already have both the final outputs together. And then I separate them and output it. So this is sort of a pretty clean way to do things. The consequence of this is that both, because this is a double pump solution, I have to spend a lot of time around the output, right? Because I have to drop this nitrogen here and then I have to drag it out. And even you can see this sort of sink as a delay. I'll explain that in a second, but uh, but the yeah, but even without that, this input command comes too early. So I can't. That's the limiting reason why I can't shorten this cycle. Because I would like to do something like this, but it's just not possible because of that. But either way, it's still um, quite a fast reactor one, and it works pretty well. But yeah, we'll also see that the spot it leaves the nitrate is sort of in a bad spot, and that's part of why I struggled with reactor 4. I think I realized actually quite late that it would be possible, I think, for me to move it to drop over here, but I realized sort of after I'd optimized things, so it didn't end up mattering. Right, so let's add my ratio in. So I do reactor 1. I do the same ratio, but I run it at 10 cycles per. Let's now take a look at reactor 2. This I do something pretty similar to what Pre does, but I have an exact, I do an exact 1 to 2 ratio with the inputs. So you can see, yeah, so what I basically do is I pretty much copied what I did in this top reactor with making the two outputs. And then I have blue, just like with what Pre did, blue kind of helps manage the nitrogen. But I also, you can see what Pre does to solve this issue of blue being in the like kind of terrible spot. What Pre did was he had red do like a loop with just nitric oxide. Um, Whereas what I do is I have red help out with making the nitrogen. I actually kind of wonder if Pre's solution might work a little better. I don't know. It's probably kind of close. I was hoping to get this to run at exactly input rate, but I actually run it at, so that this full running 2 loops of the thing runs in 43 cycles. So if we add that to our listing so far, I do 1 N2O, 2 NO, 2 3N2, 2NO2, and I do it in 43 cycles. So this is actually slower than both the last 3 reactor 2s that we've seen. So yeah, luckily it isn't so much slower, and so I'm able to stay with a good placement because of my reactor 1. But yeah, let's actually now, so yeah, reactor 3 is sort of same as usual. Reactor 4, I do, um, yeah, I was really struggling to get this first reactor to run at actual rate, or the rate that it's getting it. And so I spent a while sort of trying to find better ways to uh, input and output things quickly. Um, and so I end up doing, yeah, there's some like kind of weird things I do here. So first off, because I'm processing two at once with blue, I have the sort of like rate things end up finishing is that I have red. Uh, Essentially, if I did it in groups of two from the start, I would end like not on. Basically, the last output I'd need from here, I would be waiting on another in order to make a group of two. And so instead, what I do is I have red pick up one off the start to sort of offset it. The other purpose this serves is that it makes sure red is behind on the lower input, which is actually necessary because this is a 20 cycle loop here. And you'll remember that actually the rate of input from the other reactor is only 21.5 cycles. So I'm actually getting this bottom input too slowly. And so the way I dealt with that is that I have red have this extra delay at the start. And then everything, I specifically have the delay a certain amount so that when we get to the last output, red exactly grabs it on the cycle that it arrives. Um, so this would actually crash if the output count was increased at all, and that's just yeah because this reactor was pretty specifically set. 21.5. Sorry. That's because I do 43 cycles per this whole loop, right? And I make two nitrate per, so that gets us 21.5. So this is slower than yeah, this is faster than yours pre, but it is slower than Yellow Bunny's uh, and Juju Gulls and Darish's reactor 2. Oh, yeah, that's Yellow Bunny says maybe I should write 21.5 rather than 43 in my notes. That's fair, but I'm just writing down the ratio speed because it's helps. Yeah, yeah. Either way, it's just kind of what I'm going with. Um, let me grab something real quick. I'm realizing my laptop's, I think, going to die, so let me get a charger for that real quick. All right, let's keep going. Okay. All right, so now let's go on to check out ToughThought's first place solution, which is he names based on the ratios, the first of which we're very familiar with, um, which is taking so 0 alpha 3 beta goes to 1 psi and 1 omega. This is the same as the same as we've seen with uh, the same we've seen with the past few solutions. Right. Let's see. Right. And we'll see the speed for that in a second. And then the other, we see actually he has an exact sort of one-to-one use, and it is going to be very weird. But let's first take a look at his reactor one. So for reactor one, we'll see actually we have a handoff solution, which we haven't seen in a little while, where, but yeah, it's sort of the similar ratio. You can see there's sort of similar ways in which it's similar to a lot of the things we've sort of seen recently, where you try to, um, yeah, maybe in a way reminiscent of my solution in the way that you sort of make these two um, outputs, or yeah, you make both the outputs and then sort of group them together. Um, so yeah, it's pretty nice, but unfortunately, it's actually slower than both me and Dariush's Reactor 1 solution. So this runs in um, 11 cycles per loop. We can see that we have, yeah, a rotate here. But all right, so how is this first place if we're slower by a decent margin in Reactor 1? And that is an absolutely insane Reactor 2. So let's go through this. We have so we have something I'd say so similar to what other solutions have done with the yeah, similar to what other solutions have done with the reactor too. But we have uh, but we're gonna do something. We're gonna do some kind of different things at once. So what ToughThought does is he. So I believe, yeah, if I'm remembering correctly, blue is running mostly the same loop over and over. While where we take this one of this output and two at the top. Whereas red is going to run, I believe, let's see. Yes, so red is running, yes, let me try to remember exactly how this is working out. So red is getting those two, and then, okay, yeah, so red, well, yeah, let's actually, I think it's easiest to analyze the loops separately. So blue does this similar thing we've seen before. It's handled a little differently, but sort of runs in the same way, where we pick up these this nitrogen and then drop it off. And now let's take a look at red. So what red does is red takes every time red will take two inputs and we make this sort of structure. One of the things we can just drop off as we usually do, whereas the other we sort of do two different things. So every half the time we're going to get a nitrogen excess, and the other half of the time we're not. So what ToughThought does is he specifically bonds this onto the onto like sort of the nitrogen he's already grabbing, and that way when he goes around and makes this output, well, on one loop he just has the nitrogen extra and sort of holds it on and puts it in a nice spot, and the other loop he outputs it, and so it's sort of you could see it like we'd seen some other solutions where we'd had one nitrogen stay through, but the way that he sort of carries it around and manages to like have everything really nicely timed between red and blue is very incredible. Um, and it's actually not at input rate. It is close though. So the actual rate I believe is let me check. I think he's got it. Yeah, 66 cycles for the for this whole loop. So let's we're looking at this. This is 6N2O, 6NO, and 2, 7, 3, 4, and 3. I'm remembering correctly. Yeah. And this is run at yeah, at 66 cycles per. So that that means that we're producing one output every 16.5 cycles per the NO3, which is yeah, significantly better than the 20 cycles per output that we saw with the past solutions. So yeah, and then let's see if there's anything particularly interesting in this last solution, or in this last thing. Yeah, so you can see something, because we're getting quite quick with the top reactor. ToughThought also does something a little more complicated on the top in order to get things to the output really quickly. He also uses the fact that, actually very nicely, because the top reactor runs on a 22 cycle, or like 11 cycle loop, and this is on a 66 cycle loop. These are actually decently synced, and so that's part of why he's able to do something pretty nice here. In comparison to like the mess you see with my solution. But I guess Darius also comes up with something quite good. So yeah. Yes. Yeah. I believe. So yes. Yeah. Congratulations, ToughThought. But yes, Darius mentioned in the chat that we can merge the reactor 1 and reactor 2 and create a better solution. ToughThought, did you end up doing that? I think you mentioned it, but I know I was like hoping I was gonna get to it, but I did not end up getting to it. um, anyways, either way, he might have worked on that. It shouldn't be too crazy to merge these two solutions, though I will say that this reactor 4 actually would probably be quite a mess. Because it's actually, yeah, it's pretty. These nitrates are the nitrate molecules are very annoying to carry around. Part of why this reactor is much easier is nitrogen has free bonds, so you can like bond a bunch of stuff together and carry it. Whereas here, the only free bond you have is that you can bond this specific oxygen, which could be in a different orientation, but you can bond that specific that specific oxygen with exactly one other oxygen, and then you're at max bonds for the entire thing. So you either have to like remove bonds and then re-add them, or do some sort of mess. So, and if you do something weirder, to like bond more together, it's just a mess. So I don't know. It's probably annoying to do, but I don't know. Maybe there's a nice solution. Maybe I'm just bad at this reactor, so who knows? But yeah, let's see. Let's see if there are any interesting other. Let's see if anything I missed from what ToughThought was saying. Yeah. Yeah, ToughThought mentioned that a goal of this puzzle was to see whether different input delays would cause people to balance the equation with different coefficients. And it seems like that was with a generally resounding yes. I think you'd see this reactor 1, I'll just switch to SpaceChem. So yeah, this reactor 1, I think most top solutions move to just using the bottom output. Notably, Chichigal had his really interesting solution involving just using or using some of the top input as well. But yeah, most solutions, yeah, a lot of solutions just use the bottom. I think I know I don't know. I was really it had genuinely not occurred to me to do this sort of thing to produce nitrogen. That's part of why I think you saw my like, yeah, I have this sort of weird reactor a very different reactor too than a lot of other people did, and that's just straight up. I just didn't realize this approach. Um, I think my sort of rationale was that because all you want to do is nitrate, I just didn't see the point of inputting more nitrogen, and so I just didn't like try anything with that, and it just yeah, it meant that I missed something really nice. Okay, all right, thanks for clarifying, ToughThought. Yes, ToughThought hasn't merged them. Well, anyways, maybe I'll do that. I don't know. Probably not. Bree says the takeaway for me is that I should get better at SpaceChem. I mean, like I feel like that's my takeaway too. Um, if, I feel like but either way, it's something unfortunate to miss for me, but it's fine. Um, either way, I don't know. I just play and have fun. Sort of my general strategy. Um, but all right, let's see. There weren't many fun solutions, except as always, Yellow Bunny has a single Waldo solution to share with us. 1073, so this will be our slowest solution, but that might be expected with one Waldo. So let me see what he does. Don't particularly remember. Okay, so he does the same. I think he does the same thing for both reactors because he's not really limited by input delay. So yeah, he does the same ratio, a similar ratio to what we saw with Gall and a couple other people, where we produce 2 nitrous oxide and then 1 nitric oxide. So all right, yeah, very nice. And then this reactor, we do something nice and clean with this. And this reactor, relatively, yeah, bond the 2 together, use the fact that they're coming in at the same rate to aid the solution a little bit. Okay, nice and sweet. Yellow Bunny says, I only optimized for my time spent on this solution. Fair enough. All right, well, I think that's all to say for this puzzle. I don't think there's anything else I'm missing. Let's see. But yeah, there were a lot of different ratios people end up using. Yeah, so 5 different ones across all the solutions. Yeah, very nice puzzle. Bree says, I'm happy to have grasped the return FF idiom. Okay, I don't know what that means, gotta be honest. I haven't grasped whatever you're saying. All right. Oh, and let's now announce the puzzle for next month. So the puzzle for next month is going to be it's going to be Divide and Conquer by Yellow Bunny by vote. So let me actually we'll go ahead and release that. Should ideally be the right thing. So, what were the vote counts? It was 5-2. But yeah, it's possible people are tired of the cycle puzzle. I wouldn't take it personally, Bree. Let's see. But yeah, oh yeah, I guess I can quickly show the puzzle. I think people have seen it, but or so people here have seen it. But yeah, got carbon, hydrogen, making polyacetylene, and the metric is essentially minimize bonders times symbols. But yeah, all right. Well, thank you guys all for coming by and submitting to the last puzzle. It's fun. Yeah, it's cool to see I don't know. It's very cool to see the reactor too. I know I also feel free that I didn't spend enough time on that reactor. I don't know, most of my time was finding something nice on reactor one, and I mean that did work out, but I didn't really find great. I mean, I found something I was happy with, but the new puzzle wasn't shown. Oh, is the like export wrong or something? Let's see. No, that's right. What's the problem? The notes are shown. The notes are shown. Oh, you're right. Oh, sorry. I see what you're saying. Yes, thank you. Whoopsies. Okay, yeah. Okay, that kind of messed that up. Well, yes, the puzzle is divide and conquer. This was what I was trying to show. Thank you, ToughThought. I will, yeah, ideally, second, yeah. I need like a second screen to look at stuff for this because I'm just like frantically switching between Discord and OBS, the note thing and SpaceChem. Like when you guys can see both of them on my screen, I only see when I'm looking at this, I only see OBS on my screen. So I'm just jumping around between things. But anyways, it's a problem with my setup. Um, Maybe I'll find something better at some point. But all right, I guess I'll stop the recording here. Thanks everyone who is watching by. Come by the monthlies. Maybe they're still happening. Who knows?